Hi everyone, Mrs. Patel Dane here for topic 8.5, acid-base titrations. So we did a titration back in topic 4.6. That's where we had a burette, we had NaOH in the burette. We dripped that down into a Erlenmeyer flask of an unknown concentration of hydrochloric acid, and we had an indicator down at the bottom. So what I want you guys to do right now is go back to topic 4.6 and also into your lab notebook. You've got some beautiful notes in there regarding acid-base titrations. And what I want you to do is right over here, sketch that setup for that titration. If you don't feel like you have an adequate sketch in your notes, then go back through. There's another video from Carolina Biological that has you, that walks you through it. But essentially, the purpose of a titration is to figure out the concentration of an unknown either acid or base, knowing the known knowing one of them as a known. So we had used a formula before called MAVA is equal to MBVB. So we had, if we knew the molarity of the acid and the volume of the acid, and we knew the volume of the base, we could figure out the molarity of the base. Or if we need to figure out the molarity of the acid, we could have the other three and then just solve from there. What we're also trying to do is graph that information based upon like pretty much if we had a set amount of, let's say, HCl in there, we could put a pH probe into that flask and then drip in NaOH to see what happens to the concentration. So this next one here, we're looking at the model, and we're seeing that a 60.0 milliliter sample of 0.10 molar HCl is titrated with 0.10 molar NaOH. The pH of the resulting solution is measured with a pH meter and a graph as a function of the volume of the titrant added. So here in this graph, we're starting right over here. The pH of just the HCl at point A is about 1, pH of 1. As we are adding some NaOH, that pH, of course, is increasing until we get to a point where we skyrocket and then we level off again. So this part, if you remember, is when you had your phenolphthalein. We were trying to get to like a really light pink solution, and then one more drop of NaOH and it went to a deep pink color. And that's because as we increase the amount of NaOH, there's a point right here, a threshold, where the pH itself skyrockets. So our job here is to figure out what's happening at each of these points and be able to extract some data from this. So let's take a look at first question here. What is the titration of, and how do you know just by looking at the graph? So like, sure, they're giving you that there's NaOH there, but let's pretend that that's not there, right? You would know that you're starting out with some acid. It would have to be a strong acid. So if you remember back from topic 8.1, there were certain strong acids that you had to memorize. Go back through that list and make sure you know them. Those acids dissociate completely, meaning that they are not going to, like, they're going to completely break up, meaning that they're not going to have any more of that original acid. You know that this is going to be a strong acid because it's a really, really low pH. And that low pH, again, it's indicating that it is a strong acid. We also have a line that's fairly level right over here. When I show you guys a weak acid, you'll see the difference. So this is a titration of a strong acid. And you know it's a strong acid because the pH starts off very low. And you know we're titrating it with a strong base because if we take a look up here, it ends up being a really high amount when we have an excess amount of NaOH. So we know we have a strong base because the pH at the end is very high. We also know that this is a strong acid with a strong base because right over here at point C is our equivalence point. So that's when we're saying that we have the same concentration of hydrogen ions as we do OH ions. And that's at a pH of 7, which we know as being neutral. So we know that both of these are correct because the equivalence point is at a pH of 7. So if we write the equation for this, we have HCl plus NaOH produces, and this is going to be a strong acid, so we're going to show a one-sided arrow, produces H2O or HOH and NaCl. If we recall, Na and Cl are both, Na, and anytime Na is in an aqueous solution, this is aqueous, make sure these are all aqueous, and this one's liquid. So Na is soluble with every single ion, meaning that it will always be aqueous. We won't see a solid Na with something if it's mixed in with water. So it will always be aqueous. If we take a look at the net ionic, we can see that we have, let's break this down over here, H plus Cl minus plus Na plus OH minus. That produces water, HOH, and Na plus and Cl minus. So anything that's an ion in here is going to be aqueous. Well, if we take a look and get rid of anything that is the same on both sides, meaning the Na plus, the Cl minus and Cl minus, we can see that we've gotten rid of the spectator ion. So Na and Cl are both spectator ions. The net ionic for this is H plus OH minus produces H2O or HOH. So this is the net ionic. This is the molecular formula or equation. And then these are an ionic with spectator ions. So for C, we're looking at each point and calculate the number of moles of each ion. So we might need some space here, or we might need some extra paper as well. So looking at point A, it's only HCl. There's no NaOH added in here. So we can say that we have no no OH and no Na. If we take a look at the H+, well, if we want just the moles of H+, I'm going to bring it down here. So maybe this is point A1. So I'm going to say A1 is here for my work. I can say that I'm starting off with, it said 60 milliliters, so 0.0600 liters of HCl over 1, and I have 0.10 moles of HCl over 1 liter, and I just want the moles of H+, so I know for every 1 mole of H+, there is 1 mole of HCl. So when I do the math on this should be equal to 0.0600 moles of H+. So we will put that right in here. Oopsies, those are 2 zeros at the end. We know we don't have any OH. This is a 1-to-1 ratio between H and Cl, so it's actually going to be the same exact thing for Cl. So if we think about a model here, we might say that we are going to, let's say we have using like one of these would be equivalent to like 0.002. So like 1 H plus is equal to 0.002 moles. Same thing with the Cl, etc. So I would know I need to have 3 moles of H plus. Actually, you know what? Let's make it easier. Let's just make them each worth 0.001. So let's do all 6. 1, 2, 3, 4, 5, and 6. And I'll do the same thing. Note that these would be all over the beaker. I just want to show them like this because it kind of organizes our information a little bit better. So an explanation for this, and I'm going to have you guys write this down, not that I'm not going to put it down because I just want to make sure you're actually listening here. We have equal moles of H plus and Cl minus, and that's it because there's no NaOH added here. All right, so let's take a look at point B. Here, we've added some NaOH. In fact, we've added 30 milliliters of NaOH. So let's come over here to the OH section. In fact, let's make this B1. And I will do my work down here. B1. I have we said 30 milliliters, 0.300 liters of NaOH over 1. and that is a 0.10 molar, so moles of NaOH for every 1 liter of NaOH. Oopsies, this should be pure HCl. Then I have 1 mole of, let's say, OH minus for every 1 mole of Na plus. So that should give me 0.00300 moles of OH minus. So here we have 0.00300 moles of OH minus. We have the same amount for Na. Now we're also thinking about, some of those OHs combined with our H's. So we know we still have this stuff right in here. So let's take a look at, we have, 6, 2, 3, 4, 5, and 6. I'm now adding essentially 3 OHs. I know I also have 3 Na pluses. And I also still have my same 6 Cls. I know that Cl is, Na and Cls are both going to be spectator ions. So I'm just kind of shifting them off to the side. Hey, I can also see here, when I have H and OH in solution, they're going to combine to form water. So I have this one, and this one. So instead, I can cross those out and show instead 3 moles of H2O. So that brings us back up to here for moles of H+. So I knew I originally started with 0.00600 moles of H+. I just got 3 of them, or I tied up 3 of them with OH minus. So at the end, I end up having, if I had more space, I'd put it in here, 0.00300 moles of H+ in there. My moles of Cl have not changed. That's still going to be the same. So really, my moles of OH have actually just decreased because they got tied up with water. So really, we have 0 moles of just pure OHs hanging out. Yeah. And so here, talk about how 3 moles of H plus were combined with 3 moles of OH minus to form 3 moles of water, and you have leftover of 3 H pluses. All right, we're going to do the same thing for point C. So point C, we have, let's see, we have a total of 60 milliliters, sorry. So I'm going to make this as 0.1. And again, I'm only changing here the Na. The Na is the only thing that's changing. So 0.0600 liters of NaOH over 1 times 0.10 moles of NaOH over 1 liter of NaOH times 1 mole of OH minus for every 1 mole of Na plus. So that gives me 0.00600 moles of OH minus. So if I'm comparing that to my original, because here I added 0.003 moles of OH. I'm adding another 0.003 moles of OH. So right now I'm just going to compare it to the original amount of H plus. We can see here that our moles of OH minus are equivalent to our moles of H plus, and that's what's happening at point C. So put that down in here, and I'll actually show you right here. So the moles, or the moles of H plus are equal to the moles of OH minus. And again, we've got the same amount of Cls, but we end up with more Na pluses. And then point D, we end up with 80 mils of NaOH. And so here we have an excess of OH minus ions in there. When we do the math for that, we end up with 0.00800 moles total of OH minus. 0.006 of them were tied up with water. So I'll show that over here. So again, we want to make sure we have 6 of these. 1, 2, 3, 4. And then that means that we have 2 more of OH minus. And we still have all of those same Cls. Oh, I'm sorry. We were supposed to have 2 of those. My bad. 1, 2, 3, 4, 5, 6. And then we end up with 6, 0.0060 moles of Na plus. One, two, three, four, five, six. Cool. So looking at this, we have water, which we know is being neutral, but OH kicks up the pH to be a little bit higher. So that's why we're ending up with a higher pH at the end. And then the NAs and Cls are just spectator ions. So some stuff to know about this graph. The math. Math is fairly simple. Like it seems like it's complicated, but you're just going over from concentration and volume of HCl to the moles of H plus, which we did way back in probably unit 1, or probably not unit 1, but really close to the beginning of the year. This part, we're just kind of thinking our way through. I've shown you some subtraction, but essentially we're just trying to think of like, hey, what's happening? What's getting used up and what's left over? Now we're taking a peek at the graph. Some things that we want to make sure that we label with the graph. So one thing over here is we end up having the equivalence point. And that is when you have the moles of OH minus are equal to the moles of H plus. So here you know that for a strong acid and a strong base, your pH is going to be 7. Again, for a strong acid, strong base. We also know that, let's say over here, we have excess H plus, and over here, we have excess OH minus. So that's telling us a little bit more about our graph. As we're adding NaOH, it's changing slightly, but not too much. So it's essentially buffering the solution here. I think that's all I need to show you about with this one. Oh, and actually, let's label this. Strong acid, and make this like nice and bold. So strong acid and strong base. So there. So that way, when we refer back to this later on in our notes, you've got it. The next one. One thing I want to note, I don't know why all of these printed with NaOH as this stuff down here. Get rid of that. My bad. And who knows? I might change it. I probably won't. So here, we're starting off with a high pH. So you know you're starting off with NaOH right over there. And, we're starting out with a strong base. In this case, it happens to be NaOH. But remember, it can be any of the group 1 or group 2 ions combined with OH. So we have NaOH plus, and then when we continue adding more of this substance, so this should be HCl, it dips down fairly low. So here we have HCl, and it's the same products at the end. We have water and NaCl aqueous. When we show the net ionic, it's OH minus and H plus, producing HOH. So some things to make sure that we take note of for here. We have excess NaOH here, excess OH here, excess H plus here, and then this one is our equivalence point. You could do the math for this if you needed to, but just wanted to get you guys the idea for this. Here, oh, and let's label that. Sorry. Strong base with strong acid. Our next one. So this graph looks slightly different. So if we're thinking about back to like that first one we looked at, we know we have an acid. We're starting off with an acid here. This one, their pH was way lower than the one over here. So this one is very likely to be a weak acid. So again, a low pH shows you that this is a weak acid. So let's do weak acid. We could say the pH started low, or started, excuse me, higher. Put higher in quotes, like pretty much above 1. So this one, the pH was around 3. Another thing to show us that this is a weak acid is this little like hook right here. This little section right there is like when it kind of curves up like that, as opposed to going straight like this one. This is indicating that we have a weak acid. This one's indicating that we have a strong acid. So look for those little symbols, those little signs in here to indicate what it looks like, essentially. And then over here, the pH is going up pretty high, like above 12 or so. So we know that we have a strong base. So pH ends up high. So again, pH started higher, and let's say the hook for the weak acid, the strong base, the pH ends up fairly high. So some things that we want to take note of. We are, again, adding NaOH to this weak acid. And the pH is starting to go up, If we look at the equivalence point, it's actually above 7. In this case, it's like between 8.5 and 9. So we can say that the equivalence point is greater than 7. So that way you know you have a strong base with a weak acid. You can do the calculations as you needed to. Actually, let me go through the equation for this. So we've got HC2H3O2 plus NaOH. This will be in equilibrium because we have a weak acid. And that H plus is getting donated to, let's just say that OH. Let's get rid of the, no, I'm not going to get rid of that yet. Sorry, my bad. So we're going to say that we have C2H3O2 minus, and, yeah, I lied. I'm going to get rid of this because it just makes it easier on you guys. And that. If we're going to reverse it, it would go, that H plus would donate, that water would donate an H plus to the acetate ion right over here. So some things to look for in the graph. One, we know the equivalence point. So we know that this is when the moles of H plus are equal to the moles of OH minus. This one happens to be at a pH greater than 7 because it's a weak acid. You're not going to completely disassociate. We have some other indicators here. So some things I want to kind of share along with you guys. Let me just actually get something else out so I can take a peek. Hold on. My bad. If we look at the equivalence point, if we look at the equivalence point, halfway from that volume right over here. So the equivalence point is 60 milliliters of NaOH added. Half of that's 30. This halfway to the equivalence point right over here, so point C, is actually when your pH is equal to the pKa. And you're like, why do I care? There are going to be some questions where they ask you for what the pKa is of this. And you're going to be able to see that just from the graph. And essentially what that means is that your weak acid is equal to the amount of anions that are left over after it's been, after the H pluses have been combined with the OH minuses. We have some other things that we want to talk about as well. So right over here, this little section right there is where we have the Ka value. And then this section right over here, well, this whole area that's like fairly linear, that's our buffering region. But this is when we have excess weak base. Sorry, excess weak acid, my bad. Right over there. And if we do that, we're going to actually use something called it doesn't matter to you right now, but it will in topic 8.4. We're going to use the Henderson-Hasselbalch. So just write down like in parentheses HH next to that. That's your weak acid, and we'll revisit that in the next topic. So here we have excess of the conjugate base. And then over here, of course, is our equivalence point. And then here we have excess of the strong base, so excess of the OH minus. And for that, we can actually end up using to find the pH, if we need to find the pH anywhere in that region, we can say that pH is equal to the pOH is equal to the negative log of the OH minus concentration. Because we have excess of that strong base right over there. All right, that's a lot. I get that. Let's just make sure we label this weak acid with strong base. Okay, so another one that we're looking at is right over here. Again, sorry about this. Get rid of that part. We are starting out at a pH higher than 7, but we know it's still lower than 12, so this must be a weak base. Our equivalence point is going to be below 7, so we know that strong acid's driving that pH to be much lower. So this equivalence point, the pH is less than 7, so you know we must have a strong acid here. We also know we have a weak base because there's that little dip. That little dip is also telling you that there's a weak base, so make sure you fill those in for A. So again, to kind of label some of the things that we talked about, if we look at the equivalence point, that's 60 milliliters here. Halfway to 60 milliliters is 30. Coming up, C is going to be where our pH is equal to our pKa. And so that's when our weak base is equal to the conjugate weak acid. Right over here is like a buffering region. So we have excess weak base. We're going to use something called the Henderson-Hasselbalch equation to kind of figure out what that means a little bit later on. Over here, we have excess of the conjugate weak acid. And we also use something called the Henderson-Hasselbalch equation there. Again, this is where the equivalence point is. The pH is less than 7. And here we end up having excess strong acid. So we can use the pH is equal to the negative log of the H plus concentration there. All right, I know this is a lot. There's a lot in here. But if we can read and interpret these graphs, it makes life a lot easier. Kind of flipping over to another thing. Here, we have something a little different. So our ratio of H plus, so we have 3 H plus for every 1 PO4 minus 3. And this is, again, you knowing your polyatomic ions fairly well. So we have here a spot where if we titrate this with, let's say, NaOH, this is still going to be a strong acid. So it's going to start fairly low. It's going to start horizontally. We're going to see an increase there, then another one, to represent each of those 3 hydrogen ions that are getting donated to the base. So again, we're seeing three lifts, three sections where you're going to have an equivalence point. One is where you're going to see like the H3PO4 donate 1 H plus. And so therefore, it's going to look like H2PO4 minus. That's going to be, I probably should have written it right here. My bad. I am so sorry. H3PO4 producing H plus and H2PO4 minus. So sorry. All right. Here is we're taking this thing and then removing another H from it. So H2PO4 minus, we're removing an H plus, and then we have HPO4 minus 2. And then this section is where we're taking this, and we're saying that we have one HPO4 minus 2. We're taking away that H plus and making PO4 minus 3. So these are just the three little spots that we're going to have for this titration curve. I think like the most you need to know about this is the fact that, hey, if it's going to donate 3 H's, you're going to have 3 little equivalence points and potentially like what those equations would look like. But just start over here, take out 1 H plus. This is what you get left over. Then the next one's taking out another H plus. This is what you have left over. And then another one for the third one. So ideally you would pause right here and then draw this for the H2SO4. All right, so here we see two sections. This one is H2SO4 donating an H plus and HSO4, whoa, my bad, HSO4 minus. And this one is now taking this guy and kicking out another H plus to make SO4 minus 2. So these polyatomic, or what we call polyprotic, meaning many, essentially protons, because that's what we consider a hydrogen ion as a proton. So these are polyprotic titration curves. Again, just recognizing, hey, if you see a curve like this, it probably had 2 H's for every one of its anion. If you have something that looks like this, it probably had 3 H's for every one of its anions. This is a lot. Go back to the graphs. Try to decipher the difference between if it's starting out with a strong acid base or a weak acid base, how it's ending, if it's going to be a strong acid or a strong base, with what you guys will be doing, it would end up being a strong acid, strong base, with what you're ending with. Looking at the equivalence point, where that is, for anything that's a weak acid or base, looking at half its equivalence point to find the pH, or sorry, the pKa. Oh, my bad. So essentially, sorry, my bad. Your say your POH. No, I think I'm gonna leave it like this for right now, and then if I need to change it with you guys, I will. But yeah, so finding out where. Actually, I'm sorry. Here. This was the one with the weak base and strong acid, the question right before us. No, this should be like the pH is equal to 14 minus the pKb. I'll do it that way. But yeah, identifying those little spots in the graph are really, really important, and knowing kind of like what's in each little section. All right, I will work through this with you guys, and remember to go back through the topic videos in AP Classroom. Have a good one.